afternoon session, continuing in our theme of foundational lectures. So this is Bart Jacobs, another first-time visitor to Bellairs.
Thank you for your question, and thanks for organizing me to this wonderful place, a wonderful meeting. So some people were complaining already in the beginning of the Bart Lee and joint Lee, so I'll try and collect these Lees. So this talk will be mostly, shamelessly, categorically. And so for people who are not really into this, feel free to wander off to the beach. So I make no apologies, it will be immediately down to categorical facts. So let me start with some basic things. Kelly LaPlaza in 80, I think, proved the following fact: if C is a symmetric monoidal category, monoidal category, symmetry is not needed, that is the thing. Monoidal category, let me write this out then. Monoidal category, then the home set of endomaps on the tensor unit is a commutative monad. The fact that it's a monoid is trivial, but the commutativity is special, and I think Samson at some stage you call it the miracle of scalars. So these maps, the endomaps on the tensor unit, are often called scalars.
The miraculous part is that happens even if it's not symmetric.
Yes, precisely. That's miraculous. Now there are some strengthenings of this result. So if C also has biproducts plus a distributivity, which I will not spell out, but the distributivity of the tensor over the biproducts, then C is a semi-ring. And further, if it additionally is a dagger category, then this is an involutive semi-ring. So what I'm interested in here is the relation between this categorical structure on the one hand side and the structure you have on scalar, which is of more algebraic kind. And it turns out that there is some very nice categorical structure behind this, and it also involves monads. In the main picture, which I'll give away immediately, but which is mostly well known, if you take the category of monoids, monoids in sets, and if you take the category of monads, then there is a functor.
Two categories?
No, just ordinary category of monads. Monads on sets in this case. There is a functor going in this direction. Namely, sorry, I should write this one here. It maps a monoid to the monad M cross blank. Okay. Now in the other direction, there is a functor which maps a monad to T of 1. 1 is the singleton set here. Actually, this can be done over a category, but I'm mostly interested in the set theoretically. This turns out to be an adjunction. It's not very hard to see this, and this was already published by a person named Wolf in '73. I think it's an Australian guy, I don't know the first name, Harvey Wolf. I never heard of him later. There's another thing you can add. Let me call this rule for the category of Levere theory. I'll describe in a minute what they are. But each monad gives rise to a Levere theory. In the other direction, each Levere theory gives rise to a monad. This is a classical result in the theory of monads or equational theories. And
is there any stipulation about finite?
No, this can be done in general, and if these are finitary, you can tighten this down to an reflection over full reflection. I can't remember precisely what this is. But this holds quite generally. I'll come to this in a minute, but if you compose these, then you get an adjunction here, like this. I hope I'm doing it correctly like this. And what this does, it maps a Bellairs theory L to the scalars in here, where one is a special object in here. And you have a triangle of adjunctions describing scalars, monads and categories, explaining the title of the talk. So what I'm going to do...
Scalars.
Sorry?
Why do you say scalars?
Scalars, well, I'm generalizing a bit because here they arise as scalars. So in general, what I mean algebraic structures. And my... Yeah?
But in an albeit theory,
Yes, there are no scalars.
Okay, let me define what is a Bellairs theory. Bellairs theory L is a category with objects, the natural numbers, right? And
one corresponds
one
to
is
the
the
generic
yeah,
algebra.
precisely.
Right, yes,
yeah.
yes.
And 0 is the initial object, and n plus m is a co-product. You can define this a bit more formally, but roughly this is the best to keep in mind at this stage. What this functor is I will write it as the Kleisli category, but I'll use n as a subscript, because this category, what it does, it takes the Kleisli category, but only objects are natural numbers. So the objects here are n and n, and the morphisms from n to n are functions n to key n. Right, where I identify a natural number with the n element set. And basically, because this is a co-product, you can identify such a map as with an n tuple of terms in here. You can read them as terms with n free variables. Okay. Now this adjoint is a left gun extension, which I'm not going to describe here. It's a bit nasty, but you can still get your hands on it. And this is basically composition of this. So you take the monad, the associated monad, and then take the Kleisli. Now the aim of my talk is to change the structure I have here and look at what changes here. And I've done this work. It's sort of a game you can play. I've done this partially with Dion, and there's a paper on the archive about this, and since then, since we published the paper, I've made 2 more steps which I'll describe today. So the first part is basically recalling work with Dion. That's why the partly jumped in. Any questions about this? Is this setup clear? So let me simplify this a little bit more.
I tell you what,
Yeah.
I mean, just given the monads, is it easy to say what monads
Well, you have natural numbers, and the maps are things like this. So you have
right, so you've got a unary operator for each other?
Yeah. Does that help? Okay, let me check. Okay, I'll start with the question. I talked about this in last year when I was in Oxford about the first part, so some of the people who were there at that time are not allowed to answer this. So if I change this to commutative monads here, what changes here and here? This one is actually easy. I'll give it away. They become commutative monads. Commutative monads in the sense that Samson was already describing this morning. That is, monads on sets are strong, so you have a strength map like this, x cross y. If you have such a map, let me go with strength. You can also get a map from x cross ty. Tx cross y by simply swapping. Even more, you can get basically 2 maps like this. And commutativity says that these are the same. And the two maps is whether you do this one first or you do that one first, and then you have to do a multiplication. So commutative monads are here, and if you commutative monads here, the question is, what do you get here? Okay, they become symmetric monoidal Levere theories. So indeed we come now, since we have this symmetric monoidal structure.
Not every Levere theory is symmetric.
No, I mean with 1 comma cross.
I don't understand.
Okay, so in every Levere theory,
Every Levere theory is the symmetric monoid, right?
no.
Yeah, I'm with Jamie on that. Isn't it a finite product category which is symmetric
Monoid
monoidal?
structure is just Cartesian.
Let me describe it like this. If I have an arbitrary monad and I take a quasi-category of it, then this one is monoidal as soon as this functor is this monad is commutative. Okay. You aware of this result? And the idea
We're
is
talking about definitions really. I don't think I'm asking anything very complicated. I just want to know
what is my definition?
I thought the definition of a Levere theory was, as you gave, a Cartesian category with objects and bijections and
Yeah.
natural numbers. But then a Cartesian category is symmetric monoidal. So I don't
Yeah,
know.
but it has a second monoidal structure,
Right.
namely the one and cross, the multiplication on natural numbers is the second monoidal structure.
So you don't think Cartesian.
Yeah. So yeah, that's certain. So 0 and plus are always co-products, and 1 and times, in this case, they become a tensor structure, multiplicative structure, and also there's a distributivity between them. That comes from
This is not a product in general.
it's product of natural numbers.
It's not a categorical product.
Oh, and categorically it's not a product in general. No, that's right. Are we clear? Very good. Sorry?
Crystal.
Now, yeah, let me keep this picture, because it becomes more interesting if I put here semi-rings. And let me make it a bit easier by putting commutative semi-rings. So I have addition and multiplication, and they distribute over each other. Now the question is, what do I get here, what do I get there? And I'll give away this one. I will also give away that one. But this one is a bit more difficult to describe and a bit less well known. So what you get here is symmetric monoidal Levere theories with biproducts. And these biproducts are precisely the 0 and the plus. So in this case, the 0 and the plus become biproducts. Right? And that captures this situation. Okay? So, doing this is a lot of work, a lot of computational work, but I was happy to have a co-author on this. So we could share the work, but it's actually nice. So the next thing here is what we get here. And these are what I would like to call additive commutative monoids. The commutativity here arises because I have commutativity here. You can do this separately, but I don't want to do this here. These are the additive commutative monads. Now, this notion of additivity of these monads came up actually while doing this work, and I think this is a very useful notion, which I will try to explain next. It's the following. So T from C to C is a monad. Now maybe I'll give the intuition. The power set is an example of a additive monad, and that is because the power set of 0 is 1, and the power set of x plus y is x power set. So what it does, it maps co-products to products, and that is a key factor in this additivity requirement. And I will start to explain this a bit more generally. Okay, but this is good to keep in mind. So first, a very basic result. I assume C has co-products plus products and actually finite element. The following are equivalent. T0 so let's move to 1. 0 implies the T, which is always an initial object. So 0 is the initial object at C. Is a 0 object. So it's not only initial but also final. And 1 in the category of algebras of T is also a 0 object. It's these things, basically if you think about it, you see what the proof is. It's 1 or 2 line proofs. But it's rather smooth. Certainly, if you look at the next thing. Now, if I assume now T0 is 1, then I can always find a map so because this is the final object. Alright, and this is basically the 0 map in the classic category of the monads. I will write this as 0. What I can do now is define partial projections from x plus y to t of x. Namely, what I do is the co-tuple of the unit and 0. And similarly, you can get t2 I can take the Gleisli extension of these, put the t here, and then get them from t of this to there by posing with the multiplication. And combining, I get a map which I call VC for bi-Cartesian from tx plus y. Right, and this is the co-tuple of tp, the multiplication after tp1. Multiplication after tp2. Okay, so in this case I have constructed a canonical map from here to there, and I call a monad additive if this map is non-isomorphism. Then there is a theorem saying T is additive. Again, it says the following are equivalent. 1, T is additive, i.e. VC is an iso. Of course, for each pair x and y. The plus in the Gleisli category, I mean the operation plus the co-product on the Gleisli category, is actually a y-product. And the third part one says that the product which you have on the category of algebra, which also always exists, is also a byproduct. So basically this is a reasonably stable notion that you can characterize in several ways. So the claim is that you get this triangle of adjunctions for commutative semirings, additive commutative monads, and the symmetric monoidal Liouville theories. main example of an additive monad is, well, maybe the first one is the power set. The second one is what I would like to call the multi-set monad. Sets to sets for as a semi-unit. I guess some of you have seen this monad in one form or another. It's defined as ms of x. It's the set of maps from x to s for which the support of phi is finite. Okay, so the name multi-set generalizes a bit. People often consider this for as the natural numbers. Then it's in computer science terminology often called a bank monad, but I like to generalize this. This is a monad and it is additive. Why? Well, if I have something in here, it's a map defined on the co-product, which has finite support, so you can split it into two parts, one on x and one on y. So that is not so difficult. Why this monad is interesting, the algebras of this monad is the category of modules over S, the modules over a semi-ring. And this result then says that modules over a semi-ring have biproducts. And some special cases are, if you take the natural numbers, then modules over the natural numbers are commutative monoids. If you take S as the integers, modules over the integers are abelian groups. And if you take S as a field, let's say K, then modules over this field are simply vector spaces. So in all of these cases, this general result explains why for these algebraic structures you have biproducts.
And less than that deterministic.
Sorry?
Less than that deterministic.
Oh, sorry, yes. The commutativity
Well, I think even for non-deterministic rings, there are biproducts.
oh yeah, the byproducts are okay. Yeah, sorry, but I was thinking here of also the symmetric monoidal structure. For the monoidal structure, you need the
even for the monoidal structure, I'm not worried about symmetry and commutativity.
Yeah, I never looked into that because what I always use is this work of Anders Scott that you also referred to this morning, and that only works for symmetric monoidal. Symmetric monads, if I remember.
But the point is, alright.
So that's like for rings, you need
Yeah.
deterministicity to get tensor
Yeah.
products.
Precisely.
Yes.
Yeah. So for this, it's not needed. And actually, in this diagram, the frontal going in this direction is this multi-set construction. So far, this is the work I would. Oh no, it's not quite yet. What I also did with Dion is an addition here. If I add an involution here, so I have involutive commutative semi-rings. These become dagger, symmetric, monoidal biproduct categories, and here you get involutive, additive, commutative monads. An involutive monad is a monad where you have an handle map on it. If you do it twice, then you get the identity. So again, this works very nicely. So the next steps are, of course, can we do rings? Can we do fields? Can we do complete fields? What I can do now is rings. That is the new work I would like to sketch. And what I can also do, but I don't know if I managed to do that in time, is give a probabilistic version. Yeah.
So for each of these triangles, the category in the bottom right has an adjunction to the category at the top. That category in the bottom right, how does that stand with respect to the minimal or maximal adjunctions? Was it given the same
I
number?
never.
But it's not the category of algebras for that.
Yes.
I mean, I think of the monads that arise on the top category, which is sort of the base thing, and then whether you can then recover these or seems an important conjunction, right? Maybe it doesn't have any.
This one. Yeah, yeah. But it goes via this one. Huh? The way you construct it is taking the classic category from all. Yeah, indeed. So people have been looking at this, but not so much at
It is a
this.
classic junction of quantities.
Yeah. Okay. So rings, yes. The picture becomes commutative rings, and I still have symmetric monoidal byproduct structure, but I get something else, which I call min objects. And I'll try and explain what they are. Actually, it's a very basic notion, and I somehow assume that someone has done this before, so if you would recognize it, please let me know. So, some basic observation. If C has co-products, finite co-products, then this diagram, and this is the co-diagonal and the unique map, is a monoid. It looks a bit funny as a monoid, but it's a monoid with respect to this monoidal structure, where you take co-products as monoidal structure. Similarly, if C has products, and this is a monoid. If C has products, then this is a comonoid. It's the only comonoid you can have on this tree. Now, if C has byproducts, I get a bimonoid on X in the sort of obvious way. Basically, you combine these two things. I write this for the byproduct. I get this is the num line. This is the delta X. So this is a bimonoid. A bimonoid is not just both a monoid and a comonoid, but these maps also have the comonoid maps have to be homomorphisms for the monoid. Yeah, sure. Now, let's say X is a min object. If X is a Hopf algebra for this bimonoid. Okay, so it's a Hopf algebra for the standard bimonoid in this Hopf algebra, or sometimes called Hopf monoid. For this. So what does it mean? Can you still read this? So you do.
It's like standard twee Hopf-algebras rijst van groups.
Sorry, what?
It's like our Hopf-algebras usually rise from groups.
Yeah. Right. And there's a similar diagram here where these are twisted, but because this is actually a, I should have said, this is a commutative, everything is commutative. Actually, it's enough to have one of these. This is a minus map.
Okay.
So min objects is an object X with an endo map, minus from X to X, such that this becomes a Hopf algebra for the standard bimonoid.
I'm not requiring that it acts as a minus with respect to the commutative monoid enrichment.
That is automatic. That is derived. So the first result you of course want to prove then, that is if you have min objects and hom sets become groups. Actually abelian groups. You see what I mean? because basically, this definition says, well, recall what the definition is of the, I will recall.
What is the main object?
Sorry?
What is the main object? This is going to be a module.
It's so obvious, but somehow.
The ring
Okay.
is perfect.
We'll come to it. Let me get some figures. I write min of C for the subcategory of min objects, and morphisms commuting with these minus things. Now it turns out that they automatically commute with these minus things. And I call C a min category if each object carries such a minus.
Minus part of the structure of the object, or is it just a property there is minus?
It's a property, because there can be at most one. And recall, if you have byproducts, and each home set carries a commutative structure, which is actually unique. F plus D is defined as you do delta right? And basically what you see here then is that this says that the minus map is the additive inverse of the identity.
Is having these main objects equivalent for a semi-additive category to be additive?
I did not look at that one.
That's
but
what you would expect.
Yeah, that's probably. I did not look at additive or semi-additive categories. Yes. What you do have is, for instance, the min objects in commutative monoids is really inverse, which is sort of what you expect, eh? So the objects, commutative monoids which carry min objects are commutative groups. Also, what I can prove that modules over S, the category of modules over S, is a min category. Well, recall S is a semi-ring, and this is min category if and only if S is a ring.
So what do you mean is a min category?
The min category means each object carries a minus.
Ah, so you mean
Yeah.
mod S is equivalent to min mod S?
It's equivalent to min.
We're saying min here is a construction where you obtain a new category from the original category by taking min objects.
No, I said a min category is a category where each object carries such a minus structure.
Then it's necessarily unique.
Then it's necessarily unique, and that is because in the commutative monoid, if you have an additive inverse, it's necessarily unique. It can be at most one.
So generally min C is a subcategory of C.
Precisely. Actually, it's a full subcategory. But that is a small one. It's a full facial subcategory. There was a. Oh yeah, this. Is this plausible? So modules over S are a min category, so each object has carries a negation, and so each. Think of these otherwise as vector spaces. So you have a negation of a vector space if and only if the scalars are a ring. You have negation in the scale. Actually, there are some results saying that if C has byproducts plus also distributive tensors, so tensors distributed over these byproducts, then C is a min category. If and only if the identity on the tensor unit has a additive inverse. So in order to have on each object an inverse, it's just enough to have an inverse of one map. But this is, if you know the structure a bit, you know you can do scalar multiplication. And you can do scalar multiplication with minus of the identity, and and that gives you minus on an arbitrary object. So again, the structure on scalars is very important for structure on the whole category. And also in this case, I is identical. Because we know it's already a semi-ring, but if you have additive inverses, it becomes a ring. So it seems like a useful one. And how much time do I have, Mr. Chairman?
Gosh. So we started a bit late, so I would...
7 minutes.
Yeah, no, 25.
So how much? 25 still.
Say it all again, Bart.
You don't have to do
Say it
that.
all again.
A joke, a Dutch joke.
Yes, I'm trying to think what to do with that.
Well, we could keep to the schedule. 15 minutes.
Yeah, I can also. So what happens here is that there's also a notion of a min monad, which is sort of predictable. It's basically you get you make such a definition of that the monad is a min monad if and only if its Kleisli category is such a min category, a minus category, if and only if its category of algebras is also a min category. So that all this ties together again, and you get such a commuting triangle of such a triangle of junctions. So I don't want to go into those details. The paper on these min objects is not on the web yet, but I'll put it there soon. Of course, once we can do rings, the next step is can we do fields?
Involutive rings is just like...
Yeah, involutive rings is just because you get dagger structure here and the there. I think that this is all modular. I haven't really tried, but I'm pretty sure it is. So the next step is field, and I don't really have a clear idea yet. So this is, well, what I'm doing here is similar, but also a bit different to what Chris and Jamie have been doing, because you have some papers in which you embed the scalars into larger sets of numbers, so to say. But here I really try to translate this structure into categorical structure directly. And
Just division rings, doesn't it? This is a basis.
yeah, that could be because I have no idea yet what kind of structure fields that gives you. I've been thinking of something like dagger equalizers, but that's not strong enough to really give you division in
It's the bottom left structure that you have to find, and then the bottom right structure you can compute it.
the bottom left. No?
It's the left-hander junction which has to be discovered.
You
and
mean
then
of
the
this
rest-
one? Of this?
No, I mean the left hand of the triangle.
This one?
Yes, that's the junction is established, and the rest,
Yeah.
rest follows.
So if I take fields here, but I still have, I have to identify certain properties on those
Yes.
monads.
So perhaps that's easier than jumping immediately. to
Yeah,
the
maybe
bottom.
Depends on whether you prefer to work with monads or categories. But maybe you have some clue about what categorical structure guarantees that your scalars become a field. You've been working on this, so you're not close to this. But
I'll tell you the answer later.
yeah. Other questions?
Well, it's like I do find check problems because not everything is invertible.
Yeah, sure, that is a big problem. That is a big problem. So typically, I'm sure you will need something that the tensor unit is simple, so that you can distinguish between the zeros and the non-zeros. But I haven't found the answer yet.
Can I ask you more questions? So it's interesting that these categories and their theories, because you really expect them to form two categories. That's the
Yeah.
first thing. It's interesting that this category appears in a fundamental way in this triangle.
Yeah, but I must say the computations are already quite involved, so I'm keen to keep two categorical aspects out of it.
No, but
So
everything must do, because the other parts are only one category. So
Yeah,
you
yeah.
can form the
Yeah.
injunctions otherwise.
Yeah, that's true, but what I force here are the functors to preserve structure up to equality, not up to isomorphism.
And you don't have a hierarchy of properties in the bottom right category of Liouville theories, but there are cases where you seem to have jumped along the way. For example, you missed out braided Liouville theories or ordinary just annoyed Liouville theories. Is there any reason to think that the whole...
It's a lot of work to do. I'll still do fields, maybe complete fields, but
so I don't ask you how to work with the answers, but should one expect, when should one expect that for a particular type of Liouville theories, say a particular type of Liouville theory would extend to the rest of the triangle, or one has no idea, just has to work everything out case by case?
yeah, here I can expand a little bit of I'll do that offline. There's a bit of structure behind it, how you get to this in the monoid case, but we'll take to that. What I would like to sketch is what this becomes in the probabilistic case, because there's also some interesting structure going on there, which I think might touch upon things that Samson was talking about this morning. So I mentioned this multi-set monad in the beginning. There's also, of course, the distribution monad that Samson was talking about this morning, which I would like to describe like this. Finite support and the sum of the x of t phi x is 1. So you take, so to say, multi-sets over probabilities which have to add up to that. Now a natural question arises, if you've seen all this and seen that semi-rings play a role here, is can you put some general structure here? And that can be done, that makes sense. And what I claim you can put there is what I would like to call an effect monoid. That is a monoid in the category of effect algebras. Now, let me, before I go into technicalities, earlier we had this semi-ring here. Now a semi-ring is a monoid in the category of monoids. So we replace this by a monoid in a different category, not a category of monoids, but effect algebras. Effect algebras are roughly monoids with the partial plus operation plus a complement. So there are some formal similarities here, and the structure becomes a bit different. What you can then do is get the triangle again. On top you have effect monoids. Here you have something which I would like to call convex monads. And here convex Liouville theories. And again you get a triangle of junctions like this. Giving all the definitions is quite a bit of work, and but there is a paper on the web on this. So I would like to refer you to this. It's on my web page. What I want to do is briefly explain what these effect algebras are and the monoids in there are. And the distribution functor arises then here, but it's a distribution functor with respect to the effect monoids, like this. Okay? So what is an effect algebra? Well, I start with a PCM, that is a partial commutative monoid. I'm not going to explain really what it is, but I'll write it as this. So I have a zero element and a partial plus, which are write this encircled union, but it's not meant as an idempotent operation. It can be idempotent, but it need not be. And the main example you can keep in mind is the unit interval 0, 1. So you can add two numbers, but that's not always defined. You may jump out of the unit interval. But if you can add them, it's commutative and it's also associative in the obvious way. It's a bit painful to write that down precisely what it means, but somehow it's, I guess, obvious. Effect algebra is a PCM in which for each x there is an x per, an ortho supplement such as x is 1, where 1 is 0, supplement, this is one thing, and also and this notation, this is orthogonality, is defined as follows. So it's a sort of compatibility relation which often occurs in quantum settings. And indeed, these notions have been introduced by Fowlers and Handel in their work on studying effects or observations. And I find them interesting because they combine logic and probability in a same notion, and that can give rise to some interesting combinations. Let me give some examples. So 0, 1, of course, where the complement is 1 minus half. Another example is if you have a Hilbert space, the effects of the Hilbert space are the endomaps which are between 0 and the identity. This is in a certain sense generalizing this. Right? For each abelian group, if you take take an element in there and you look at such an interval, you get an effect algebra. Also each orthomodular lattice is an example of such an effect algebra, in particularly closed subspaces of a Hilbert space in which you do standard quantum logic. And there's also Boolean algebras are examples. So with my PhD student Jorik Mandelmaker, I had a paper last year in QPL in which we proved that the category of effect algebras is both complete and complete, and also has a symmetric monoidal structure. And this symmetric monoidal structure is interesting because then you can consider, for instance, these kind of things. That's a tensor of the unit interval and a power set Boolean algebra as a tensor of effect algebras. Now these tensors are a bit awkward to precisely understand what they do, but if you stare at this sufficiently long, you'll see that these are the step functions. So these are functions which are constant on certain subsets. So you get interesting structures coming out by combining probability and logic.
Bart, are the tensors the thing what you want them to do in most cases? Like if you take your Hilbert space, projection lattice is the resulting...
No, it's not the case that if you take the projection lattice of a tensor of Hilbert spaces that you get the tensor of that is not the case.
So yeah, so it's not really the one you want. Oh yeah.
But this one is canonical in the sense that they capture bilinear maps in the usual way. But if you have a tensor, you can say what is a monoid in the category of effect algebras, right? And those are precisely the structures I'm interested in. And an example is then 0,1 is an element of the monoids of effect algebras. Yeah.
But you probably, I remember in our files that is maximum and minimum tensor products, and the real one is somewhere in the middle. Is this the maximum or something? You may not know that.
No, I don't know that. But it's a bit messy world, these tensor products. But this is, the one we use here is fairly canonical, and those are the kind of things we want here. So 0,1 is a monoid in here. That's what I want to do. I'll make a short digression. I mentioned this Jori, this PhD student. Because you have a tensor and a monoid, you can also look at what are modules in effect algebras. So there are actions with respect to this monoid. If you take the category of effect modules with respect to 0,1, there is an interesting duality with convex sets. And so convex sets you can describe also as algebras of this distribution monad. And this duality is interesting, and is Jori studying when this gives rise to an equivalence. And
So what do you mean by duality?
oh, sorry, it's a dual adjunction. Sorry, a dual adjunction. Thanks. Yeah. But what I want to go to is he's studying when this is actually a duality, and so he has defined something which he calls a Banach effect module 2, in which a certain norm is complete in a suitable sense. So you get standard duality like for rings and C-star algebras and compact Hausdorff spaces. It's comparable to the duality that you have there in this setting.
And the condition of the complex.
Yeah, that's what he's still struggling with. But at least on this side it's very clear what it is. On this side it's more subtle. There is
You mean if you start with one of these bad things go and then you come back to where you started?
So in a sense it's enough to characterize it on this side, but on this side it's not so clear yet. But you do have a standard topology on convex sets, and you have to formulate the condition in a suitable way in terms of this topology. So, but then you get the Gelfand style duality in this setting. What I want to finish with, and then there are unfortunately many loose ends, but hopefully you get some ideas of this talk, is that if I have certain effect monoids, then I can define a distribution functor with respect to this effect monoid, and define it as those maps from function 5 from X to E, for which the support is finite, and you require that now this joint exists and is equal to 1. And using this definition, you can get a triangle of adjunction, and therefore you have to characterize this monad, and it turns out to be an affine monad. And also it satisfies certain convexity properties, which I will skip here, which are fairly technical, which you can find from here. So again, also the message here is that also in this probabilistic case, this triangle of adjunction comes out fairly naturally. So I think that is a fundamental structure relating some basic notions in mathematics and basic algebraic structures of monads and structures of categories. And that's it. Thanks for listening.
Any questions?
So I mean, just at the very last point, I guess the normalization condition is related to it being affine.
The normalization,
Yeah, the summing to 1. that's
Yeah,
actually
precisely.
where that's reflected.
Yeah, yeah, yeah.
And the triangles of the junction, so the right bottom is logically, if you're using them more or less as just combinatorial type of things.
Yes.
And the logical aspect is somewhat, I'm not sure if it's missing, it's not being brought out. Anything to say on that?
And what you mean by logical aspect? What you really
People mean usually use logic theories to look at models and
Yeah.
dimensions.
In that sense, yes.
Satisfying.
Yeah. In terms of algebraic theories, precisely what that is. Yeah, that's true. I've not made that precise. There's
Is
still
there
work
anything
to
to be said, you think?
Sorry?
Is there anything interesting to be said?
Probably. But I've not done it.
I mean, presumably there might be interesting features about the categories of algebras arising in different situations as well.
Yeah, yeah, that's true. Certainly you can look at the categories of algebras of these monads. So here I only looked at the Chrysler category, and it might be that those categories of algebras are precisely the ones that are captured by the DVF theories. That would be possible. Like in the when you start from semi-rings, you get modules over those semi-rings, and maybe that's precisely what's captured there. So there's still more work to do.
Lots of things to do.
More questions, remarks, suggestions? Has anyone seen these min objects? They look so obvious to me. No?
So if you represent byproducts in terms of these bioalgebras, it is a complete, well, does this necessarily give you a byproduct structure if you ask them to be bioalgebras? Because that's kind of connected to whether this additional Hopf algebra structure would make the graph from semi-additive to additive.
Yeah, yeah. That's
It's different,
possible.
it's an elegant representation.
Yeah, I think so too. And if you look at what Freud has done in terms of his abelian categories, he formulates abelian categories in terms of structure on the Hom sets. He says the Hom sets should be abelian groups. But with this, what's here in terms of min objects, you can describe this structure purely categorically in terms of objects and arrows, and not in terms of its arrangement. Of course, it's equivalent, but maybe that's the reason they have not been brought out explicitly.
Okay, thanks Bart again.
Yeah.
Start in 10 minutes.